In this chapter, we will look at a number of proof techniques. Let us start with looking at an implication. So we have in the first case a statement P, which implies a statement Q. So here we have an implication, and we want to prove that this implication is true. So we want to prove that if P is true, then also Q is true. So implication means P implies Q, or also said as if P, then Q. Some examples might be, suppose we have two numbers A and B, and we know that A and B are positive, and A is smaller than B. If this is the case, then we also know that A squared will be smaller than B squared. Another option, suppose that X is a positive number, so here we have a number X which is positive, then there exists another real number a number Y such that X is Y times Y plus 1. So if we look closer at this second example, we can write it more mathematically. So here we have X. So for all X which are real numbers, if X is positive, then this means that there exists another real number Y such that X is equal to Y times Y plus 1. So we have a P statement. The P statement here on the left side, X is larger than 0. And on the other hand, we have the Q statement here. So this is what is being implied. So if P is true, so if X is larger than 0, then Q is also true, which means in this case there is a real number such that X is Y times Y plus 1. Then just for clarity, so this V, this means for all. So for all in our case X in R. And then the other one, the inverse E, means there exists. So there is something that is. First option for a proof is a direct proof. So a direct proof has the following idea. Basically the idea for the direct proof is that we assume that P is true. And then we just show that Q is true. So this is the most straightforward way of proving anything. So you just assume that one thing holds, and then you use this information, so you use what you know from P to prove that Q is also true. So if we look at the second example, so we have P is true, so we know that there is an X in R such that X is positive. Then what we have to do is we need to find such a Y. So we need to find Y in R such that Y times Y plus 1 is X. So if we can find such an Y such that this equation holds, then we have proved that Q is true. The question is just which Y exists such that X is Y times Y plus 1. So we have to solve this equation, solve the equation for Y. What you could do is you can look at it. So this is Y squared plus Y minus X equal to 0. You would take the discriminant. Discriminant is 1. So you consider it as an equation in Y. And X is just a constant in this equation. So it's 1 minus 4 times minus X. So we get 1 plus 4x. We know that x is positive. This means that 1 plus 4x is positive. So the discriminant, we can take the square root of it. So there are two solutions. So y is -1 plus or minus the root of the discriminant, so the root of 1 plus 4x, divided by 2. So this is a real number because x is a real number. And so we found two solutions for y, and we only have need for one. So one solution was enough. We have found two. So there is a y such that this equation, the equation y times y plus 1 is equal to x, holds. So here we prove that there is such a value for y. For the following, let's take another example. So this is our third example. Suppose that n is an integer, so n in z, and you know that 3n plus 2 is an odd number, then n itself is also odd. So if we translate this to mathematics, if we write this mathematically, here we say that for all n in z, for each integer in z for which that 3n plus 2 is odd, so all the integers for which 3n plus 2 is odd, then, so this implies that n itself is odd. So we have a p statement on the left, a q statement on the right. The way that we will prove this is by contraposition. So proof by contraposition. For a proof by contraposition, you will basically look at the inverse statement. So we have a statement, P implies Q, and this is actually just the same as saying not Q implies not P. So why is this true? This is a direct consequence of logic. If I have a statement which implies another statement, then if the other statement is not true, the first statement cannot be true. So we just inverse the reasoning, we negate the reasoning. So P implies Q is just the same as not Q implies not P. So we will start from not Q, and now we will show that not P is also true. For the example, it means that we have an n in z, so we consider that n is an integer, and we also consider that Q is not true. So Q is not true means that n is not odd, so n is even. If n is even, then you can write that n is equal to 2 times k for some k in z. We now need to prove that 3n plus 2 is not odd, so we have to prove that 3n plus 2 is even. So we will take a look at 3n plus 2. We know that n is 2 times k, so it's 3 times 2k plus 2, so it is 6 times k plus 2, which is clearly an even number. Why? This is 2 times 3k plus 1, so it's divisible by 2, it is an even number. So 3n plus 2 is even. This corresponds to not P, and so this concludes the proof. We started from not Q, and we have shown not P. So we started from, let's assume n is even, and then we showed that 3n plus 2 is also even. For the following proof, consider this example. So we have, in this example, two real numbers. So suppose that x and y are real numbers, and also suppose that x squared plus y is equal to 13 and that y is not equal to 4. Then it holds that x is different from 3. So mathematically, what this statement says, so for all x and y in R, so for all real numbers x and y, we know for these real numbers that x squared plus y is 13 and y is different from 4, if this is true, then x is different from 3. So here we have the P statement on the left, we have the fact or the part that we know, and then on the right, the Q statement, the part that we have to prove. The way we will prove this is a proof by contradiction. So in this kind of proof, what we will do is we will look for a contradiction in the case. So we will assume that P is true and also that Q is false. So we assume that the left side is true of my statement, but that the right side is not true. We then have to show that this is impossible. So we have to show that it's impossible for P to be true and Q to be false. So this means we have to find a contradiction because of this statement. So we assume in this case, for the example, we assume that P is true, so we assume that x squared plus y is equal to 13. We assume that y is not equal to 4. And then we also assume that Q is false. So Q is false means that x is actually equal to 3. So if we then take the first equation and the last one, we replace x by 3. So this gives me 9 plus y equal to 13, or y is equal to 4. However, we have an assumption that y is different from 4, and we have here from the other two assumptions that y has to be equal to 4, so we found a contradiction. So this is not possible. And so it's impossible that P is true and Q is false in this case. So here we proved that if P is true, then Q is also true by contradiction, because we found a contradiction in the statements.